There are some general properties that make the structure of the carbohydrate different, or that are very important to know when we are studying the structure and different isomers of the carbohydrate, like the chiral atom. In this section, we will discuss about all of those properties. We will discuss about the asymmetry carbon atom, why this asymmetry carbon atom is important. We will discuss about the Van 't Hoff's rule of N, that what is this rule and how we use this in the structures of the carbohydrates. Then we will discuss about the epimers and the anomers, that what are actually they and how they are different from each other. Starting with the asymmetric carbon atom, that is also known as the chiral carbon atom. Asymmetric carbon atom is basically a carbon atom, a central carbon atom that is linked to the four different atoms. As we know that valency of the the valency of the carbon is 4, and carbon attach 4 atoms to itself. When all of these 4 atoms are different from each other, then the carbon atom will be known as asymmetric carbon atoms. Reference molecule is glyceraldehyde. We can take the example of the glyceraldehyde. Glyceraldehyde is basically a carbohydrate that consists of 3 carbon in its structure. Number of stereoisomer can be found out by the formula of the 2N. In case of asymmetrical carbon atom only. Here, this is the example of the asymmetric carbon atom. You can see this is the carbon that is attached to the 4 different groups. Now, not in case of the carbohydrate, but this explains you the concept of the asymmetric carbon atom. This is the chlorine, fluorine, bromine, and hydrogen atom. All of these 4 different atoms are attached to the central carbon atom. Now, because of this asymmetric carbon atom, there is the possibility of the stereoisomerism in the carbohydrate. As you can see, the orientation of this group is here. It is different, and here it is different. This stereoisomerism is basically due to the difference in the spatial arrangement of these atoms around the asymmetric carbon atom, and that give rise to the stereoisomers. So basically it is this stereoisomerism, or the number of the stereoisomer, is based on the presence of or the number of these asymmetrical carbon atoms. That is better explained by the Van 't Hoff's rules of the N. Van 't Hoff said that the number of the possible isomers of any given compounds depend upon the number of the asymmetric carbon atoms the molecule possesses. For example, if and this N represents the number of asymmetric carbon in the formula of the 2N. For example, if a molecule of the carbohydrate, if it has 2 carbon atom in 2 asymmetrical carbon atom in its structure, then the number of the isomers that it will have is 2N. 2 multiplied by 2, it will be 4. So a carbohydrate that have 2 asymmetrical carbon atom in its structure, it will have 4 stereoisomers, and a carbohydrate that have 3 asymmetrical carbon atom in its structure, it will have 6 stereoisomers. Similarly, if we discuss about the simplest known carbon atom, or the case where there is a presence of only 1 asymmetrical carbon atom, then there will be 2 possible isomers, or the stereoisomers. Coming to the epimers, when sugars are different from one another only in configuration with regard to a single carbon atom other than the reference carbon atom, it means that the arrangement of the molecules in the space that we just had discussed, if this difference is only in the 1 carbon atom, then we will say that these sugars are known as epimer. But this carbon atom should be different from the reference carbon atom. Now, reference carbon atom is actually the carbon atom just next to the aldehyde group or the ketone group. You can say that the second last carbon atom is known as the reference carbon atom. Here, let me explain you this with the help of example. As you can see, this is the glucose and this is the galactose. Now, both of these sugars, they have 6 carbon in their structure, and you can see that both have similar arrangement. Aldehyde at the end of the structure, hydroxyl group is present here, here, same cases here and here as well. But the only difference in the structure of the glucose and galactose is the presence of this hydroxyl group 1, 2, 3, 4 at the 4th carbon atom. At the 4th carbon atom, this hydroxyl is arranged to the left side in case of the galactose, whereas to the right side in case of the glucose. So as this glucose and galactose, they differ only in this at the single carbon atom in the configuration. Therefore, both of these are known as the epimers because of the difference in the configuration at the carbon number 4. Now, if we take the example of this D-mannose and D-galactose, although both of these are also the 6 carbon atom containing carbohydrate, but you can see that they do not differ at only one carbon atom. You can see the difference that they differ at carbon number 4 as well as they differ at carbon number 2. So basically, because they are not differing at only one carbon atom, that's why they are not the epimers to each other. For them to be epimers, they should differ in configuration only at one carbon atom. And D-mannose is also the epimer to D-glucose as they differ at the carbon number 2 only. Now coming to the anomers. Anomers are basically the compounds that have an anomeric carbon in their structure, and because of the presence of this anomeric carbon atom, the arrangement of the molecules around them is different. That makes them different from each other, and this anomeric carbon is basically different. This anomeric carbon is basically different from the epimers. Here, in case of the carbohydrate, this is basically the anomeric carbon that is responsible for the formation of anomers. This is the open chain formula of the carbohydrates that we usually write, and this is the Fisher projection or the Fisher formula, and this is the Haworth formula that is actually the cyclic form of the carbohydrate formula. And this, because of this anomeric carbon, the carbohydrates forms the anomers. Basically, due to the presence of this anomeric carbon, there is the formation of the anomers that we have discussed in the first section, that the alpha and the beta, the alpha glucose and the beta galactose, we have mentioned that they are anomers. So also in form of the glucose, in glucose we have both alpha form and the beta form. These alpha and beta are basically anomers to each other because of the presence of this anomeric carbon. And now the conversion from this straight chain structure to a cyclic structure is basically when there is a formation of bond between the oxygen atom to this anomeric carbon atom. That result in the formation of a cyclic structure, that in case of glucose, or when there is a presence of 6 carbon, that is known as pyranose, because it resembles in structure to a pyrene ring. And in case of the 5-membered carbon or cyclic structure, it is known as furanose because it resembles furane in its structure. So that was all about this section, in which we discussed about some general properties of the carbohydrate. We discussed about the Asymmetrical carbon atom, that it is attached to 4 different groups, and due to this attachment or due to the presence of this asymmetrical carbon atom, there is a formation of different stereoisomers. And we discussed about the epimers, that is basically due to the difference in the configuration of the at only single carbon atom other than the reference carbon atom. And then we discussed about the anomers and the anomeric carbon atom that result in the formation of alpha and beta anomers. So that was all about this section. Thanks for watching scardia.com.